All right, so in this video, we're going to be looking at Stokes' theorem and doing line integrals via this theorem. So we can see the definition of Stokes' theorem here is the line integral of f dot dr is equivalent to the area integral, where we are doing the curl of the field dotted with the gradient of the surface that is bounding the path that we're following. So let's look at surfaces where this applies that are not just the flat xy plane. Because if this is just on the xy plane, then this gradient g function is actually just the k vector. But it can apply to other cases where maybe our surface is actually in 3 dimensions and there is some other surface that we can follow. So let's consider, for example, other kinds of surfaces may also be equivalent to the surface, to a more complicated surface, or could be thought of as being in the xy plane. Now, one example might be something like a paraboloid. If we are doing the surface is our paraboloid, when it intersects with the xy plane, it intersects in a circle of radius 3. So one thing that we could do with some of these problems is we can actually swap out the surface to make our algebra a little bit easier. So if we have some equivalent curve, again, if it's the boundary of the paraboloid intersecting with the xy plane, we could just use the xy plane rather than the surface of the paraboloid. So there are other possible functions that we can sometimes use. Again, we should not get a different answer by swapping out those surfaces as long as the boundary region is the same in both cases. It's just that the math is going to be more difficult if you're using the paraboloid as your surface rather than the xy plane. So it's something to keep in mind. So let's consider Stokes' theorem to calculate the line integral f dot dr. Here is our field, and the surface is the paraboloid we were just talking about, 9 minus x squared minus y squared, where z is greater than or equal to 0. So notice z is greater than or equal to 0. When this thing intersects with z, that's where you get that circle of radius 3. So, but let's do this. So the first thing for our Stokes theorem is we need to calculate the curl of our field. So we're going to use our curl notation, and we're going to calculate our partial derivatives for all of the various components of our F field. And when we do that, our I component, the derivative for Y, knows the derivative for Z. In the J component, we've got our derivative for X is 0, the derivative for Z is 2Z. And then in the K component, the derivative for X is 2, derivative for Y is 0. And so we get this as our curl. And then for the GXYZ, as I said, we could put everything on one side of the equation to find our G. And then we take the gradient of that to get our component, and we end up with 2x and 2y and 1 from our z. And so this is the upward pointing gradient. We could also use the downward pointing gradient, but typically you want to be pointing into the region that's bounded. So if we want to integrate over the surface, we're going to need to replace both these vectors and any resulting dot product with just 2 variables. So we're going to replace any z's in the equation with the surface that we solved for z. So that would be our paraboloid. So in this example, our curl, we have a z in this component. So we're going to replace that with our 2 times 9 minus x squared minus y squared. And distributing the 2, you get the 18. And then our del G is already only in terms of X and Y. So that's the only substitution we had to make. And then we dot these together, component by component. We get 4xy, and then this one times this, and then this one times that, and then this one times that. And we end up with this expression in some form or another. And then this is the function that we have to integrate over the two-dimensional region. And then, of course, because this is a circle in the xy plane, this is a circle of radius 3. So we would convert this to polar. So we don't have to use those nasty square roots. And so then that would give us this expression. So our 4xy, x is our cosine theta, and y is our sine theta. So we get this, and then all of the rest of this algebra. The x squared plus y squared, part of the reason I left it like this is that this is just r squared. So that's where we get this 4r cubed from. Times 4y is going to get us the extra r and the sine. And then that's our 36 r sine plus 2, then r dr d theta. So we distribute the r all the way through, and then we integrate. And when we integrate this, we end up with this becomes r cubed. So that's the 81. And then this becomes essentially 12r cubed. This is r to the 4. R cubed becomes r to the 4th. And then this one becomes 12r cubed. We end up here. And this becomes 4/5 r to the 5th. And then this becomes r squared. We plug in our 3's, and we get this crazy expression. And then we've got some sine terms we can combine. And then we continue the integration for theta. And then we end up with, this is a substitution that we get sine squared from. Sine becomes cosine, 9 becomes 9 theta, and we plug everything in. These all end up canceling, and we just end up with 18 pi. Now, again, the thing that I mentioned before was that you don't have to do the surface that they give you if there is another equivalent surface that covers the same boundary. So let's think about our circle of radius 3. The area of that circle of radius 3 is 9 pi. And it turns out that if you use that surface instead of the this parabolic surface, this paraboloid surface, what you end up with when you do the area of that region is you end up just integrating 2, because think about our field here. If you just use that XY plane, that circle in the XY plane, the vector that is perpendicular to that plane is just K. It would be 0, 0, 1. And that means dotting 0 with this thing, you would get 0, and dotting 0 with this thing, you would get 0, and dotting 1 with this thing, you would just get 2. And 2 times the area of 9 pi gives you 18 pi. So we did all of this algebra, and we didn't need to, because if you had chosen the XY plane surface and not the parabolic surface where they have that shared boundary, you would get exactly the same answer with much, much less work. So this is one of those important things to, again, think about. Just because they give you the surface, yes, you can use the surface. And if it's oriented at a weird angle, then yes, you kind of have to use it. But if you choose your surface to actually be more carefully selected, Maybe you can swap out another one that has a similar boundary that is easier to work with, and you won't get stuck with quite this much work to do in order to get the same answer that you would get with something similar. Now, it's always a good idea when you're learning this to practice the problems as given, but if you can make that next step to replacing one surface with another simpler surface, you can really save yourself a lot of time with these Stokes problems. And that is one of the power of Stokes theorem, because you don't actually care which surface it is. As long as the boundary is the same, then you can replace one surface with another surface and still get the same answer.